Welcome back to Decentralized Application Development Crashcasts. I'm Sheila, and I'm here with Victor to dive deeper into the fascinating world of P2P networks. Before we begin, I'd like to remind our listeners that if you're enjoying our content, please rate us on your favorite podcast platform. It really helps us reach more developers like you.
Absolutely, Sheila. Your support means the world to us. Today we're continuing our journey through Chapter 2, Fundamentals of P2P Networks. We've already covered the overview of P2P systems and unstructured networks, and now we're moving on to structured networks.
That's right, Victor. And to kick things off, I have a quiz question for our listeners. Are you ready?
I'm always ready for a good quiz. Let's hear it.
All right, here goes. In a structured P2P network with 1 million nodes, what's the typical maximum number of hops required to locate any piece of data?
Ooh, that's an intriguing question, Sheila. It really gets to the heart of what makes structured networks special. Without giving away the answer, I think our listeners will be surprised by how efficient these networks can be. It's a great way to highlight the power of structured organization in P2P systems.
I agree, Victor. Now, before we dive into structured networks, let's quickly recap some key terms. We've talked about P2P networks, which are systems where participants, or peers, share resources directly without a central server. And we've discussed unstructured networks, where peers connect somewhat randomly. Is that correct?
That's a great summary, Sheila. Now let's turn our attention to structured networks. Can you give us an initial definition of what these are?
Sure, I'll give it a shot. From what I understand, structured P2P networks are systems where peers and data are organized in a specific predetermined topology. This organization allows for more efficient routing and data lookup. Is that on the right track, Victor?
That's an excellent start, Sheila. You've captured the essence of structured networks. To build on that, I'd add that this predetermined topology often takes the form of a distributed hash table, or DHT. This structure allows peers to efficiently locate data without having to flood the entire network with queries.
Interesting. So how does this compare to the unstructured networks we discussed earlier?
Great question. Unlike unstructured networks, where peers connect randomly and data location can be challenging, structured networks provide a systematic way to organize both peers and data. Think of it like the difference between a library with books arranged randomly on shelves versus one using the Dewey Decimal System.
That's a helpful analogy, Victor. So in this library analogy, how would we represent the concept of a distributed hash table?
Excellent question. In our library analogy, the distributed hash table, DHT, would be like the card catalog system, but distributed across all the librarians. Each librarian, or peer, is responsible for knowing the location of a specific range of books. When you need to find a book, you don't have to ask every librarian. You just need to find the right librarian who knows about that particular book's category.
That makes sense. So how do peers in a structured network know which other peer to ask for a particular piece of data?
That's where the magic of consistent hashing comes in, Sheila. In a structured network, both the peers and the data items are assigned unique identifiers in the same address space. This is typically done using a hash function. The network is then organized so that each peer is responsible for a certain range of these identifiers.
I see. So if I'm looking for a specific piece of data, I would hash its identifier and then route my query to the peer responsible for that part of the address space.
Exactly. And here's where it gets really interesting. The routing in structured networks is designed to be very efficient. In most structured networks, like Chord or Pastry, you can reach any peer in the network in O log n hops, where n is the total number of peers.
O log n. That sounds efficient, but can you break that down for our listeners who might not be familiar with Big O notation?
Of course, Big O notation is a way to describe how the performance of an algorithm changes as the input size grows. In this case, O log n means that as the network grows, the number of hops needed to find data grows much more slowly. For example, in a network with 1,000 peers, you might need about 10 hops. But in a network with 1,000 peers, you'd only need about 20 hops. It's this logarithmic scaling that makes structured networks so powerful for large-scale systems.
That's impressive. It reminds me of our quiz question. Speaking of which, could you give us some examples of real-world implementations that use structured networks?
Certainly. One well-known example is the BitTorrent distributed hash table, DHT. It's used for peer discovery in BitTorrent networks without relying on centralized trackers. Another example is the interplanetary file system, IPFS, which uses a Kademlia DHT for content routing.
Those are great examples, Victor. Now, I'm curious about potential drawbacks. Are there any scenarios where structured networks might not be the best choice?
That's an insightful question, Sheila. While structured networks are excellent for efficient data lookup, they do have some limitations. For one, they can be more complex to implement and maintain than unstructured networks. They also tend to be less resilient to high churn, that is, peers frequently joining and leaving the network.
I see. So there's a trade-off between efficiency and flexibility. And could you explain what you mean by churn for our listeners who might not be familiar with the term?
Absolutely. Churn refers to the rate at which peers join and leave the network. High churn means there's a lot of turnover in the network's membership. In structured networks, this can be problematic because the network needs to constantly reorganize itself to maintain its structure. And yes, you're right about the trade-off. It's always about choosing the right tool for the job. Structured networks shine in stable environments where efficient data lookup is crucial. But for more dynamic scenarios or when simplicity is key, unstructured networks might be preferable.
That makes a lot of sense. Now, as we're nearing the end of our episode, I think it's time to reveal the answer to our quiz question. Victor, would you like to do the honors?
I'd be delighted. Remember, we asked, in a structured P2P network with 1 million nodes, what's the typical maximum number of hops required to locate any piece of data? The answer is about 20 hops. This is because of the O log n routing efficiency we discussed. Log base 2 of 1 million is approximately 20, which means you can reach any node in a network of 1 million peers in about 20 hops or fewer.
That's truly impressive. To wrap up, let's summarize the key points we've covered about structured networks. 1. They organize peers and data in a predetermined topology, often using distributed hash tables. 2. They use consistent hashing to assign identifiers to peers and data. 3. Routing is highly efficient, typically O log n in complexity. 4. Real-world examples include BitTorrent DHT and IPFS. 5. While very efficient for lookups, they can be more complex and less flexible than unstructured networks. Did I miss anything important, Victor?
That's an excellent summary, Sheila. You've captured all the key points. I think our listeners now have a solid understanding of structured P2P networks.
Great. And to our wonderful listeners, remember that your engagement means everything to us. If you enjoyed this episode, please visit crashcasts.com, join our Discord community, or support us on Patreon. Your feedback and support help us create better content for you. Until next time, happy coding.